researcher. Welcome to Quantum Mechanics Done Right, the shortest path from novice to researcher. This is a book that is forthcoming from Springer Nature, and I anticipate it's going to come out sometime in 2025. On the left, you can see a picture of an oil slick off the coast of Santa Barbara that I took on a trip to actually look at the naturally forming oil slicks off of Santa Barbara. And the phenomenon that gives those interference patterns is a quantum phenomena. In the center, you can see an animation of a classical Stern-Gerlach experiment, and that's just one of the different experiments that we'll cover in this book. In Quantum Mechanics Done Right, we take a new vision and a new viewpoint as to how one should learn quantum mechanics, and we do it in a very different way. And I hope through this video series and through the book, you will enjoy learning quantum mechanics in this fashion. Quantum mechanics is one of the highest achievements of humankind and the most accurate scientific theory ever. Yet only an exceedingly small fraction of people actually understand what quantum mechanics really is. We can try this as a Fermi problem. Estimate how many people do you think actually know quantum mechanics. I would think a high estimate would be maybe about 200,000 people in the United States have taken quantum mechanics, and that would bring us into probably 0.05% of the people actually understand what quantum mechanics is, less than 1 in 1,000. I think that's a real shame. This is something that I'm hoping we can change. But learning quantum mechanics is hard. There's nothing that can be done to make it easy. And I'm giving you here some quotes from a class that I taught that's a sophomore level relativity and quantum mechanics class. And these are some of the responses of students who took the class. And I'll read some of the select quotes for you. This course will most likely cause you to question your choice for a major. Enjoy the relativity part of the class because that is probably the last thing you will understand. When you get to quantum, there will be a long period of time where you will feel like you have no idea at all what is going on. This class is tough, especially when you get to the quantum part, but don't freak out. This class is difficult. Relativity is not too bad, but quantum is really hard. This course will drain you and make you regret studying in this field. Be forewarned, be prepared. Flee now and leave, O ye of weak mind. Read no further unless you are ready to put 150% into quantum. All right, so these comments are really not that different from what other instructors are doing, and I think that they show that we are not doing a great job. If you're a pessimist, you can say maybe it's just me who's not doing a great job, but I don't think it has anything to do with the instructor. It really has to do all with the material. The way that we teach quantum mechanics is not very easy to understand. But it doesn't have to be this kind of rite of passage. We're not medical doctors who force continuity of care. We don't have to make our students go through what we went through just because that is how you do it. We should rethink how we teach quantum mechanics. So how did we get into this state? The legacy actually comes from Oppenheimer and David Pines, who was a student in Oppenheimer's wartime and early post-war quantum mechanics classes at UC Berkeley, wrote about this. He said, Oppie's course on quantum mechanics was justly regarded as a classic. We now possess not one but two written accounts of them in the form of excellent books written by his students, Leonard Schiff and David Bohm. Although both books were based on those lectures, they couldn't be more different. Bohm captures the philosophy and the poetry, Schiff the formalism. Now, if you actually look carefully at these two books, Bohm's book throughout is actually incredibly similar to Schiff's book. And in fact, if we didn't know that they both came from the same source, we might think that they were plagiarizing each other. The only difference is Bohm has an extra chapter on measurement where he discusses some very interesting concepts, and that's what's actually made Bohm's book famous. But in terms of instruction, it's Schiff's book is the one that rules, and nearly everyone follows the Schiff paradigm. Here are pictures of David Bohm on the left and Leonard Schiff on the right, along with copies of their textbooks, which I'm sure most of you have seen or are familiar with. As quantum instruction moved from an advanced graduate course, back in the Berkeley days, this wasn't even an introductory graduate course, it was an advanced course, to an introductory sophomore class, the instruction has never changed. We still use the differential equation-based approach. Why? It's not because we don't have new quantum textbooks. I went around and I looked at all the quantum textbooks that were released around 2021, I believe is when I did this. And here's what I found. This isn't even all of them. This is just a selection of the quantum books that were available. It's almost never ending. And yet, when you look at them, nearly all of the prefaces start out the same. To paraphrase them, they read something like, "There's so many quantum textbooks on the market that one would be crazy to think of writing yet another. However, I believe mine is different and thereby worth the effort." Then when you look at it, they're essentially a clone of this Oppenheimer, Bohm, and Schiff paradigm. I'll have a lot more to say about that in a later video where we do some comparisons between recent textbooks and the Oppenheimer, Bohm, Schiff paradigm. Now, in the United States, we teach quantum mechanics to students 3 times. We teach it the same way each time, and they still don't get it. There's a famous saying attributed to Einstein that insanity is doing the same thing over and over again and expecting different results. Now, in reality, this doesn't come from Einstein. It comes from Alcoholics Anonymous brochures from the mid-1980s. Yet the sentiment is still the same. It asks the question, are we insane? So how do we do quantum right? I don't want to make a video that is just complaining about things are so bad and everything is awful and how are we ever going to make any progress? I actually decided to do something. So the first thing we should do is we should make it accessible. We should make it so you don't have to have taken many years of physics and many years of math just to be brought to the table to learn quantum mechanics. The second thing we need to do is provide a conceptual understanding. For those of you who have studied quantum mechanics, I'll ask you bluntly, do you feel like you have a conceptual understanding of it? Or do you feel like you've learned some math rules that you could apply? And yeah, I can apply them, but I don't really understand what they mean. We need to focus on the physics and not the math. Most students who take a quantum mechanics course will say, I really loved it. It was a lot of math. In fact, it felt more like a math course than a physics course. Well, shame on us. It shouldn't. We're physicists. Let's teach the physics and focus on that rather than the math. Another thing that you learn if you go into research and do a PhD is most of the quantum mechanics that you learned in all of this instruction over the 3 years isn't actually what you'll use when you get involved in research. Most research involves working with operators, and you learn how to do things like solve differential equations with series solutions, which never comes up in actual research anymore. So, let's teach ideas that can actually be used in modern research. Let's discuss modern experiments. Many quantum classes will start with the experiments that led us to quantum, and then they'll ignore the fact that we're now deep into the second quantum revolution, and there are lots of exciting new experiments that are at the frontier of knowledge, but we don't cover them. Why is that? Let's use a representation-independent formalism. When you took classical mechanics in your freshman year, the instructor spent a lot of time teaching you that a vector is not the 3 numbers that represent it. It's an abstract object, and you could use any coordinate system that you want. Yet when we get to quantum mechanics, we always work in the position representation. That's not the way we should do it. We should work with a representation-independent formalism. And doing so, we can actually reduce our calculations to manipulations that only involve 4 fundamental operator identities. And I'll have more to talk about that in this series. All right, let's go into a little more detail. How do we make it accessible? We teach quantum ideas using only high school level math. This means algebra, geometry, trigonometry, and complex numbers. It requires no calculus. You heard me right. You can learn through graduate level quantum mechanics with no calculus. And no, it doesn't mean that everything is done with matrices and linear algebra. There are some linear algebra ideas that are needed, but those can easily be developed along the way as they're needed. And surprisingly, you'll find there aren't very many that are actually needed. We're going to teach the quantum concepts first. We want people to be able to reason quantum mechanically. That includes understanding what superposition means, understanding what measurement means, understanding what complementarity means, understanding what entanglement means, and understand what tagging means. Tagging is when you create an entangled state in a reversible way where you can reverse the entanglement. These 5 concepts, just by working with these 5 concepts, you can actually analyze many of the modern experiments that exist. And this is exactly what we do in the book that I have developed. The first 4 chapters focus just on conceptual ideas and enable you to think conceptually about different quantum experiments. We also want to focus on physics and modern research. Quantum is an experimental science, so we actually have to teach the experiment. For those of you who've taken a quantum mechanics course, let me ask you a simple question. Did you ever learn how to measure momentum? You probably learned that you can't measure position and momentum at the same time, which actually is not correct. You probably learned that when you talked about the uncertainty principle, but you were never told how you actually measure momentum. Don't you think that's odd? Don't you feel like maybe you were swindled in your quantum class? Well, in my book, we show you how that's done and many other experiments as well. How can single quanta be measured? Have you even thought about this? What do I do if I want to measure something that's the smallest thing possible? How do I actually measure it? How do I get a detector that can actually probe something that is so small? This is a concept that you need to know if you're going to learn quantum mechanics. Let's describe important experimental developments that led to the second quantum revolution. We can now control individual quanta. How do we do that? We should be teaching that. Let's provide tools that are useful when you go beyond your quantum mechanics class and you want to work in quantum field theory or many-body physics, or you want to be able to read the literature on that. Let's provide you with tools that allow you to do that in the instruction that you're actually taking. We're going to use a representation-independent formalism. All mathematicians will tell you this is the way all theory should be developed. Surprisingly, quantum mechanics is one that isn't developed this way. We're going to develop the abstract reasoning. So this is one of the things that makes quantum mechanics hard. You have to be able to reason abstractly. If you cannot, then you will not be able to do quantum mechanics. But it's a process. Anyone can do this. You just need to be taught how to do it and become comfortable with it. So that's one of the things that we do. And finally, we perform all of our calculations using just 4 fundamental operator identities: the Leibniz product rule for commutators, the Hadamard lemma, the Baker-Campbell-Hausdorff formula, and the exponential disentangling identity. Those of you who've taken quantum mechanics before have probably heard of the first 3, but most, unless you work in quantum optics, have not heard of the 4th. And the 4th is critical to be able to have a full suite that allows you to actually do things using an operator-based approach. We're in the second quantum revolution. Here I'm showing you an STM, that stands for scanning tunneling microscopy, of a quantum corral. Each of those pointy things are metal atoms that have been placed in a circular pattern, and then that ring-like pattern inside is the quantum mechanical electron probability wave distribution. And these are the kinds of things we can do now in the second quantum revolution. You can make a quantum corral and observe the properties of the quantum corral with a scanning tunneling microscope. On the top, we have the surface of silicon. That is the first thing that was measured with an STM back when it was invented in the early 1980s. Another really cool thing are ion traps. Those little spots are individual atoms. Let me repeat that. They're individual atoms. They're being observed via something called a cycling transition. And what you're observing there is a movie of a chain of atoms that have had their center of mass motion excited, and that's called a phonon. And we're observing that phonon mode oscillating in a movie taken with snapshots using this cycling transition. That is like one of the coolest things to imagine that you can do this. When you were taught probably in high school that you can't image individual atoms. Well, there you go. We're imaging individual atoms. It's not correct. Another really important second quantum revolution idea is the GPS. This is a quantum mechanical sensing application that no one can live without anymore. The GPS, you should be able to understand how a GPS and atomic clocks work. And then finally, we have the most incredible engineering marvel, the Laser Interferometry Gravitational Wave Observatory. There are two of them, and they're used to measure gravitational waves, measuring to 1 part in 10 to the 20 to 1 part in 10 to the 21, which is just an unimaginable sensitivity. And they observed the collision of black holes in a gravitational wave, which is shown here. This is the first observation of a black hole merger. This is what the second quantum revolution is, and this is what you should be learning about in your quantum mechanics classes. Hey guys, let's do quantum right.